Most tactile servoing systems in the literature rely on position-based tactile servoing, where a contact pose is first estimated from the tactile image and then used for control. While effective in controlled settings, this strategy is fragile and can be limiting in some scenarios. Direct visual servoing in image space offers an attractive alternative, as it avoids explicit pose reconstruction or sensor modeling. However, when applied naively to tactile sensing, it breaks down due to strong, location-dependent illumination effects produced by the sensor's fixed LED configuration. These photometric variations violate the brightness-constancy assumption required by image-based control, leading to unstable or divergent behavior. To overcome this limitation, we introduce a direct tactile servoing framework that operates purely in tactile image space, enabled by a learned photometric normalization that restores luminance consistency and makes direct control feasible on real hardware. The key lies in how we taught the UNet network. For every real sample, we paired the sensor's RGB input with a corresponding canonical gray map as the ground truth target. This forces the network to learn a color correction that strips away the directional lighting effects, recovering the underlying contact geometry. We found that training on asymmetric shapes creates contradictory signals. Rotating the object changes the lighting profile in ways that confuse the network. Spheres, however, are rotation invariant. By training exclusively on balls only, we bypass these inconsistencies. This strategy simplifies data collection and offers the optimal trade-off between training effort and real-world performance. Here we show our proposed direct tactile servoing framework in action. Notice how the robot tracks the target smoothly. This stability is possible because our learned normalization actively corrects photometric errors, stabilizing the image stream and allowing the controller to converge rapidly toward the desired contact location. In contrast, using standard grayscale conversion on the same task produce false motion signals. The controller misinterprets these lighting changes as object movement, leading to severe jitter, drift, and ultimately a complete loss of contact. To evaluate the robustness of our direct tactile servoing framework, we compared it against a standard position-based tactile servoing controller. The visualization is organized into columns, each corresponding to one of the methods, and each one is shown for two different robot configurations. This side-by-side layout enables a direct comparison of how both controllers respond to identical tactile inputs as the robot attempts to regulate contact. The final column presents the tracking error evolution. In two cases, both approaches successfully converge. In another two cases, the pose-based controller stabilizes but cannot fully converge, remaining trapped in a steady-state offset due to biases introduced during pose estimation. In the remaining trials, the pose-based method fails to initialize because the contact geometry does not provide enough overlap for a reliable pose estimate, and the controller never enters a meaningful regulation phase. Our method, by contrast, remains unaffected by this limitation and continues to converge in all cases. The error plots make these differences clear, highlighting the broader basin of attraction and superior convergence achieved by our direct image space formulation. We now demonstrate full 6D tracking of random movements produced by a user. 5 different objects have been used, including those that would produce tactile imprints with multiple contact points, holes, and multi-holes or symmetries. The system successfully regulates position and orientation simultaneously, maintaining stable contact across complex trajectories, diverse objects, and varying materials. Finally, the proposed framework demonstrates significant resilience to physical sensor damage. Because direct tactile servoing operates on dense, global pixel information rather than sparse feature points, the control law allows the appearance of defects across the entire contact surface. This property allows the system to remain functional even in the presence of local artifacts such as the broken gel surface shown.